So, oh, earthquake, hold on. Okay, we're good to go. So first of all, one of the things that I was showing was this concept of diffraction. So what happens with Miraj Sharif? We can see it. Oh, yes, they saw it. Amazing. Great, great, great. So basically, one of the things that I wanted to show was the concept of diffraction, which is basically the spreading of a wave when it passes through a gap equal to or smaller than its wavelength. And it also happens when a wave hits an edge, right? So when it hits an edge, you get this thing going on where diffraction only happens at the side, but the rest of the wave doesn't diffract. And one of the most important things when you draw this diagram is, number one, you have to show diffraction properly, and number two, the wavelength here, lambda, must be equal to the wavelength here, lambda, all right? Make sure you draw nice diagrams. Basically what happens is you have to keep the wavelengths the same. So that's one thing. And then the next thing that you need is the concept of interference, right? We're going to talk about interference really quickly and really simply right now. So say we have two waves coming along from different places and they meet up. So say we have a wave like this, and say from another place, another wave comes and overlaps or superimposes on this, and they meet up like this. So what happens is these points on the wave will add up. And when they add up, they make a bigger wave like this. Whoops, it's supposed to have the same wavelength. So it's going to be like this. So basically the amplitude is going to be twice of those. So this thing where they're meeting in phase is called constructive interference. And the second thing is that there's another way that these waves can meet. Say a wave comes along like this, and another wave, I'll just use a dotted line here, meets it like this. So what will this result in? It will result in this thing called destructive interference. Why? Because when it's a maxima and when it's a peak and a crest and trough, sorry, when they meet, which way would the resulting wave go? No direction, because they're going to cancel each other out. So this is destructive interference. So we can simplify these 2 points. When waves are meeting in phase, we call it, what do we call it?
Constructive.
Yes, constructive interference.
You're going to catch me off guard. Actually.
Oh yes, you're going to fall asleep else. And when they're meeting anti-phase, yeah, we call it destructive. See, I didn't ask you that. But I will ask you, is the next question.
No.
What phase difference is anti-phase? Can you tell me that?
Me? Is it 180? Is it 90?
Oh man, it's 180.
180,
What the hell, man? You did say 180.
Yeah.
Then why did you change it? Why did you change it? Be confident about your answers. That's one of the most important life lessons. Be confident. Fake it till you make it. Except for in physics class. If you fake it, I will know. So, so yes. Destructive interferences are always out of phase, right? Destructive interferences are always a specific out of phase, which is 180 degrees. Other than that, anything else is out of phase other than being in phase, exactly in phase, which is constructive interference. But destructive interference will occur at 180 degrees specifically. So that's the second concept that you have to be aware of, all right? So based on these two things, diffraction and interference, we can go into double slit diffraction. That's all you need to know, really, if you want to understand double slit diffraction nicely. So what we're going to do is, say, for example, I start with a gap, right? And we have a wave passing through the gap and it diffracts, right? Nicely diffracts. And then I draw another set of gaps, slits, where it diffracts at both of them. And the reason I diffracted it first here is so that when the waves meet here and here, they're meeting in phase. So basically a crest being emitted from here is exactly when a crest is being emitted from here. Same exact wavelength and same everything, so that you understand it nicely. So basically you get this thing going on, all right? So you diffracted 2 points. So if we had a screen here to show how the diffraction is, then what you would expect to see would be that this would create a bright point here, and this would create a bright point here. So if I draw a graph sort of thing, the higher the graph is, the brighter it is. Then you'd get a bright point here, and then it drops down in brightness like this. And then you can get the same thing here. You get a bright point here, and then it drops down like this. This is what would have been expected. And honestly, this is what we should have seen. But the funny thing is, this never happens. That's right, Matsuzo?
Yep.
Yep. What do we see? Can you tell us?
It's your central fringe.
Oh yeah, we see this crazy pattern. Can you describe this crazy pattern?
Come on, man.
Well, you can try. Come on. Believe in yourself.
Very large central fringe.
Yes, you get a central maxima, a really bright central maxima. Excellent. What do you get after that?
And then dark spots, and then again maxima.
Yes, basically you get bright and dark spots, right? So this is not exactly what you see on the screen. This is us just representing the different bright and dark spots. If you were to see this on the screen, what it would look like is basically you'd get a really dark, really bright spot here. The pen ink represents bright spots. This would be dark, and then a slightly less bright spot here, and then again dark, and another bright spot, and then another bright spot, and the same pattern here. So you get this central, really bright pattern in the middle first. This is our central maxima. And other than that, the others are just a little less bright as we go to the sides, all right? So this is what we see when it comes to double slit diffraction. So the important thing is we have to explain what's exactly going on. So I'll try to explain it once here, if you can see and understand what's going on. So what happens is, along this line, we see this interesting thing where the crests of one wave meet to the crests of the other wave. Because this is hand-drawn, it's not exactly perfect, but it's as close as we can get. So this shows that along this line, you're getting this thing which is constructive interference. And basically we have the crests of waves, oops, can't see that. We have the crests of waves meeting at the crest of another wave. So these are all points where we have crests meeting crests, right? And what happens when crests meet crests? Yes, you get constructive interference. So these, all of the rings I'm drawing, the circles, these have points where crests meet crests. So you're going to get constructive interference. Very good. What are you going to get here, Maqsadul?
Destructive wave.
Wrong. You're going to get constructive interference because it's a trough of this wave and the trough of this wave. So yes. Yeah.
You got it right. I was testing you.
Yeah. Oh, you're testing me. Good job, Maqsadul. Good job, Maqsadul. All right. We have a question. Is this the same as Young modulus double slit experiment? All right, I don't. Young modulus is something related to the material's behavior, physical properties of how hard and soft and stiff and all of these things is. This is basically Young's double slit experiment. All right, it's not Young modulus. That's something to do with stress, strain, and everything, forces and extension. So anyway, moving on. If we have this line here, you're going to see that you have the crest of a wave and a trough of a wave, trough, trough, crest, crest, trough, trough, crest, crest. So you get a line of constructive interference all along this. You get the same thing along this line, you get the same thing along this line. But between the lines, you get something else. You get the crest of a wave plus the trough of another. So if we were to extend our pattern that we drew here, you'll see that you get another line of constructive interference along here. However, between the two, you get crests and troughs meeting with each other, which means this is what? Destructive interference. And that represents one of these dark spots. And again, we get the bright spots. We're going to do this maths again because it's really important that you understand it crystal clear. So I'm going to show it from a very different perspective now. I need all of your attention. So I won't draw the patterns here. What I'm going to draw is the paths that they're going to take. So say, for example, if we take the point here, what happens is a ray of light is being emitted from this slit. Let's call this slit 1 and let's call this one slit 2. And a ray of light travels from this slit. So what I've drawn is an isosceles triangle, by the way. So what happens is, if we were to draw little wavelengths to show how the waves fit on this path, 1 wave, 2 waves, 3 waves, 4 waves, 5 waves, all right? So how many waves do you expect on this side, Maqsadul? 1, 2, 3, 4. Would be cool if I just drew a little more now and just throw you off. Like, oh man. Anyway. So yes, you get 5 lambda on this side and we got 5 lambda on this side. So what happens is when the waves meet, it's basically what? One of the first things I showed. It's a wave like this meeting with a wave like this. Right? A wave like this plus a wave like this. So what does this lead to? It leads to constructive interference. So, all right. So constructive interference. So we get this bright spot here, right? This is the creation of that first bright spot, the central maxima. Right? And that's why it happens, because they're meeting in phase at this point. And this happens at this point. Now, if I shift a little to one of the sides, say I go to this point, an interesting thing happens. I can draw a straight line from slit 1, and I can draw a straight line from slit 2. Maqsadul, do you want to sit on this side? It will be easier for you to watch.
No, do you want me to look at the comments and stuff and then help you out?
That's fine too, but if you're enjoying, do whatever you like to do.
Yeah, I'm okay.
You good? Okay, that's great. So, wholesome guy. 1, 2, 3, 4, 5. That's the first time I've ever said something nice about you. Yeah, I know. Anyway,
and
so
I have it on camera. Yes.
Oh, you have it on live.
Yeah.
Oh, damn, man. All right. So from this path we have 5 lambda. We're going to ignore that. What I'm going to do is from this path 1, 2, 3, 4, 5 and a half. All right. So I tried drawing 5 and a half. So this interesting thing happens here because this path is a little longer than this path. This path is approximately 5.5 lambda, while this path was 5 lambda. So what happens here is the waves which meet no longer meet in constructive interference, because it's basically a wave which is like this meeting with a wave which is like this. So this will lead to what? Destructive interference. So you don't get a bright spot here, you're going to get a dark spot here. So you get a bright spot here, and the brightness drops to dark here. If we move on a little further, if we go down here, what happens is you have a path which is even longer, right? So this path would be, say, 6 lambda, and this path would be, say, 5 lambda again, just to keep stuff simple. So what happens here again is that the path difference is 1 whole lambda. And what does this lead to? It leads to the same waves again, this meeting with this. So as a result, what do you get? You get a bright spot again. So if we go even further, this thing continues. We can even write down an entire table for this. So how would the table go? The table would go as follows. Let's first draw the entire pattern that we would see on this side, and obviously we would see it on this side also. So first we can write the path difference, right? The path difference will lead to what? It leads to a phase difference. This phase difference would lead to what? An interference. And this interference will lead to what? A pattern, bright or dark. Right, so from here, moving on. So the path difference is basically what? Here, we take this point, the path difference is 0 lambda. We're going to express the path differences in lambda. So if this is 0 lambda, what will this phase difference be, Maqsadul?
What? Phase difference?
You fell asleep, didn't you?
I did.
So path difference 0 lambda, what's going to be the phase difference which this results in?
Are you going to ask me again?
Okay, it's going to be 0 degrees.
0 degrees.
Yes. Why? Because the path difference is 0, so there's no difference when the waves meet.
Exactly.
They're in phase. Yeah, sure. So the interference is going to be what? Constructive. So if you have constructive interference, what are you going to see? You're going to see a bright spot. All right, if we move a little bit to this side, down here, if we move here, what do you see? You see a path difference of half lambda, right? Because, like, you know, this path and this path would have that sort of path difference, which leads to a phase difference of how much?
90.
Oh, dude,
180.
180. Why do you make the same mistake twice? 180 degrees, and 180 degrees path difference will lead to what? Destructive interference. Yeah, and that leads to a dark spot, D-A-R-K. Moving on, if we go down to here, what do you see? You get a path difference of 1 lambda, phase difference of 360, which effectively becomes 0, which makes it constructive again. So what do you see? A bright spot. Moving on, what do you get? 1, you're going to get 1.5 here, you're going to get 2 here, this is 2, then you're going to get 2.5 lambda, right? And the last one, the last bright spot is going to be 3 lambda. So this is going to be 360, this is going to be 360 plus 180, this is going to be 360 plus 360. I'm just breaking them down so you understand where they're coming from, 2 lambda, right? And then 2.5 lambda is going to be 360 plus 360 plus 180, and 3 lambda is going to be 360 plus 360 plus 360. And the interference is going to be what? Constructive. Here it's going to be destructive because there's a 180, there's a half, there's a constructive, this is going to be destructive, this is going to be constructive, then again you're going to get a dark spot, a bright spot, a dark spot, and a bright spot. So we can reduce this into a sort of relationship. What is the relationship going to be? Anywhere where the path difference is n lambda, anywhere when the path difference is going to be n lambda, you're going to get constructive interference because the phase difference is 0 degrees. Anywhere where the path difference is n lambda plus half lambda, you're going to get destructive interference because the phase difference is 180 degrees, right? So you get bright spots and dark spots. Oh man, this is getting all like, oh man, lots of dirt. All right. This entire thing has this one equation that I need to talk about in the next few minutes. The equation is lambda is equal to xs by d. This can be written as as by d, xs by d, doesn't really matter, but this is the equation. And what are the relating factors between them? If we go back to our heebie-jeebie pattern here, lambda is the wavelength, very straightforward. X is the fringe separation, right? The distance between one maxima to the next. This is x. Maqsadul, you ready for a question? So what is S? Can you tell me what S is?
That's the distance.
Oh nah, poor guy didn't sign up for this. I just dragged him here, so not his fault. S is slit separation. It's basically the distance from one slit, midpoint of one slit, to the midpoint of the other slit. So it's important that you mention midpoint because say I draw 2 slits like this, right? It's going to be the distance between these two, and it's going to be this. If I was to draw a small slit and a wide slit like this, slit separation is still going to be this distance, midpoint of one slit to the midpoint of the next, right? Slit separation. And D, can you tell me what D is, Maqsadul?
A distance.
Yeah, very good. This is distance from the slits to the screen. This is basically D. So these four factors are related with this equation. Lambda is equal to XS by D. Please learn this equation and know how to use it. Sometimes they love asking what's going to happen to the fringe separation, the maximas, the distance between the maximas, if I change other factors in my situation. So the best thing to do here is make X a subject of the formula. X becomes lambda D by S, and that makes it really easy. If you increase the wavelength, fringe separation increases. If you increase the distance between the slits and the screen, X increases. If you increase the slit separation, make the slits move further apart from each other. Oh, we're going out of focus. All right. Oh man, it's focusing on my hand. All right, yes. If we move between the slits, if we make the slits move further apart, then fringe separation decreases, right? So if this is the only thing which is inversely related. If this increases, then this decreases. If this decreases, then this increases. So basically, this is the equation you need to know. And really quickly, I'm going to tell you the sort of questions they love asking. They're going to ask questions like, what's going to happen if I increase the brightness? Well, what's going to happen if you increase the brightness is the bright fringes become brighter, right? But the dark fringes are still completely dark. Maqsadul, can you tell me why they're completely dark?
Because it's destructive.
Yes, it's still complete destructive interference. So that basically means the dark fringes still remain absolutely dark. That was the first situation where I increased the overall brightness to both slits. Second is, what if I increase the brightness of one slit and not the other? Or basically that can be asked in a slightly different way. If I make one of the slits wider and keep one slit the same, what do you expect to happen then?
That's a question.
Yes.
I think X idea, it's gonna get brighter.
Dude, that's rookie mistake, man. Rookie mistake. How are you going to do this stuff? How are you going to go to MIT if this is the sort of answers you're going to give? Basically, the thing is that it's all right. It's all right. I won't tell anyone you didn't get into MIT.
Don't mention my name.
Joking, guys. You're going to hear about this guy very soon. Anyway, he's going to be the next Nobel Prize winner. Inshallah. Inshallah. Everyone dreams of that, don't they? Anyway. So, going back to the stuff that I was saying. If the brightness of one of the slits is increased and one of them is kept low, then what happens is you get the brighter fringes becoming brighter because more light is entering the experiment. However, the dark spots don't become completely dark. There's some light which still stays there. Why? It's because you have destructive interference, but it's incomplete. Why? Because from one source you're getting a lot of light, and from the other you're not getting so much light. Unequal amounts of light basically will lead to unequal amounts of destructive interference. And that will lead to the points not becoming completely dark. So how do you write that? You say that the bright fringes become brighter and the dark fringes are not completely dark. They slightly become brighter. And that's because of incomplete destructive interference due to unequal amounts of light from the two slits. Other than that, they might ask you the regular stuff. What's going to happen if I increase the slit separation? What's going to happen if I increase the distance between the two, and these sort of things. And then they're going to ask you stuff like, this is the value of X. Then give me a good idea of what this is going to be, that going to be. And so just as an estimate, the wavelengths are going to be in nanometers. Obviously, visible light is within the range of like 450 to 700 nanometers. And so basically that's going to be the wavelength if we're going to do visible light. If we're doing visible light, the distance between the slits is going to be something around 0.1 to 1 or 2 millimeters. That's going to be slit separation. The screen should be like a meter apart. And also the bright fringes that you're going to get here, the distance between them is going to be at most maybe a centimeter or so. So yes, that's that. We're done with that. And that's exactly what we were doing all of this time. And that's AS double slit diffraction for you right there. I hope you guys got that. It was really fun. Thank you guys for giving your time watching this stuff, and again thank you Maqsadul for joining us today. What?
So don't mention. Ask questions.
Yeah. Do you guys have any questions? Anyone? Any questions? You can ask right now. Any questions? Anyone? No questions? No questions. Do we have no questions? No one has any questions. Thank you. Yes, thank you Sadia. Thank you Miraj Sharif. Thank you too. Finally understood this. Oh yes, this is the happiest moment that a teacher has, when they realize that a student who was having difficulty understanding something understands it. So yes, thank you for that. Thank you for giving your time to understand this. I am so happy. Alright then. So see you guys again. We're going to be doing this tomorrow night again. If you guys have any opinions about what you want to watch tomorrow, just send us a message on the page and I will try to help you with that. Oh, we have a question. Why does the brightness decrease in the observed pattern? I got a question. Oh, yes, I saw your question. On the sides, that's because diffraction has this thing called a diffraction envelope. So basically the entire diffraction, maximum light reaches the central point. And as you move further away from it, the amount of diffraction decreases the amount of light which reaches the screen. Sometimes in some books, you're going to see something like, a curved screen. And in curved screens, what they're going to show is that the diffraction pattern remains the same throughout. So that's basically because the distance from the screen and the walls stays equal. So in such patterns or in such books, you're going to see a pattern which doesn't decrease at all, just keeps on going like this. But for your A levels, it's all right to know that this is how it's going to be. The central maximum is going to be the brightest, and because it's within the diffraction envelope, as you go towards the sides, they become less bright. That was a good question. Thank you, Kazi Ryan. So, thank you guys for your time and everything. Alright, one more question. Samin Sabah. Does the power difference always increase by half lambda, or is this just an example? Well, as you move from one maxima to the next, it slightly varies, right? So, from here it's 0 lambda, and by the time you reach here, it's going to be 1/2 lambda. So, as you move slightly along this path, it slightly increases from 0, and then at one point, it's going to be, sorry, not this point, this is going to be half lambda. So, basically, it's from 0, then maybe like, 0.1, 0.2, 0.3, 0.4, 0.5. And then again from here 0.5, 0.6, 0.7, 0.7, 0.8, 0.9, 1. And then like that. That's how it is. Right guys, my A2 students are waiting. I'm seeing them coming and watching this video. If you have any further questions, please feel free to share with us on our page. And we have this wonderful team ready to take your questions. Take care guys. It was wonderful explaining it. Thank you Maxwell for everything. And I'll be back in a minute for A2.
Bye.
Bye bye.